Hi and welcome. I hope everyone had a nice break. So our next session is with Dr. Mirko Kempf and Eric Tussino from ecolytiq, and they'll be talking about structural graph analysis with property graphs. So handing over to you.
Thank you very much for that, for the introduction. Hello, everybody from Germany. We saying good evening already. And welcome to our talk. We want to talk about the recycle rather than mine structural graph analysis with property graphs. And we would like to share a little bit more about our background. So our interest in this issue stems from our current work at ecolytiq, where we support consumers to better understand their environmental impact through enriched financial data transaction. And we aim on using data from publicly available data assets because for us, it is important to support people to live a sustainable life in a transparent and reproducible way. Assuming we could provide an integrated view, which covers the aspects of at least some of the 17 SDGs, we wanted to know how well could we support decision makers in making sustainable decisions. For this, we need then the information of context of a location, a product, or a business partner. But however, many of today's data problems are not pure technical, but rather topics which are relevant to our society. And hence, we use existing technology and available data for structural graph analysis on property graphs. And instead of collecting our own data, we follow the community spirit and focus on collaboration. So how did we get here? We once started out to measure and analyze biases in the representation of knowledge in one of the biggest public knowledge bases, Wikipedia. So we also measured how much the users are interested in those topics over time. And for this, we defined a metric which we called representation index to provide a context to the page click time series.
So what is a representation index? It is a normalized value of a measurable property of a thing, for example, a Wikipedia page or any other network node you can imagine. In order to normalize this measured value, we divide it by the average of the same value obtained from an ensemble, which is in the next neighborhood of that network node. And this allows us to do a structure-dependent normalization. And as we see it, it is a context-sensitive normalization, which takes not only the direct measured data into account, but also data from other related and interrelated things. So we use this representation index as a metric to compare the representation of topics in individual Wikipedia languages. And this can be an indicator for public acceptance or the majority of a topic. And why is this relevant? Data quality is a critical aspect in any data-related project, and we have seen strong representation biases for topics and how they are covered by Wikipedia. We expect such biases to exist in other digital systems and also in their datasets as well. And if we can't fix it, we should address the variation in data availability and data quality in future data integration projects. So in order to learn more about representation of SDG-related information in public data assets, we work with a graph data model to study, manage, and use public sustainability data. We simplify data integration and data blending using a multi-layer graph model, and this approach has shown to be very practical in our previous projects.
So what were our assumptions? Let's take a look at let's have a look at the available data sets illustrated on the left. So we look at customer data, at OpenStreetMap data, real-time, and sensor data and other data, context data. Initially, we assumed that many public open data sets are available and that it's easy to integrate all of these open data assets for complex data analytics. And we expected that integrated data provides a homogeneous input for a variety of algorithms. The result should be then to be able to easily compare. But what we observed was that in reality, those assumptions of what should be there were disappointing. Everywhere we saw differences and gaps in formats, data models, and ontologies. Many public data assets were isolated, and integration of such public data is not as easy as we thought, even in today's modern data platforms and cloud-based solutions. And in order to overcome these barriers between the application and data domains, that was then to get our next goal.
So the reality gap we have observed is shown here in the slide. We would expect lower cost and less effort due to all the learnings, but the more data one wants to integrate, the more problems we have to handle. And even if we use RDF and Sparkle, it is still a problem for cross-domain data integration. The technical standards are there, they are used, but the way how they are used differs depending on the domain you are in. And because we need data from multiple domains, we could use RDF format for storing triple data and for reasoning, but a common data model which fits to the requirements of analytics algorithms is still not available in this context. So we stepped up and decided to build such a data model which allows us to do data projection and to use common protocol standards for scaling the operations. And this is very important, not only to be able to integrate on the metadata level, but also on the content which is described in such a data asset. And hence we look into scalable cloud technology to solve the problem on the technical level.
So as soon as we hit this reality gap, we became aware that this is not just our problem for the specific data analysis of sustainability data, but that it addresses fundamental issues formulated in the FAIR Data Principle Initiative. FAIR standing for the majority principle of findable, accessible, interoperable, and reusable. Our specific problems addressed every aspect of the FAIR data principles, so we decided to lift our problem out of its current domain and come up with a solution that would be able to address the shortcomings to the principles rather than a quick fix to our immediate problems.
We went out to solve the problems using a multi-layer graph, and we created a management tool for such a graph structure using two great cloud services. The PyGeoCube project allows us to combine geospatial data and also the analysis with temporal data and combine it with structural analysis on either highly integrated data or specific projections of it. So let's recap. We identified two types of problems. Some are addressed by the FAIR data principles, others are addressed by PyGeoCube tool using cloud-based streaming processing and a graph database, and both scale very well. We wanted to avoid the hassle of cross-domain ontology mappings. Instead, we integrated the data assets on the metadata level. We manage the data streams in layers, or the data assets in layers. So our layers form a property graph, and multiple layers of the property graph can be combined. The idea is we take data from arbitrary systems. If they offer a Sparkle endpoint, we use Sparkle queries to define the content of a layer. We do the semantic data mapping on the fly while the data is collected and integrated into the graph structure. And this way we can use static data assets, and we can also combine real-time data streams which are blended into this multi-layer graph structure.
So in many cases, people focus on metadata-based integration of domain knowledge. For practical application, one has to cover both dimensions, data models and data flows. And since working with large data assets on scalable cloud-based systems is no longer magic, we can use a variety of tools to integrate data assets across domains.
Our example data model contains two data assets. We have two domains. One is OpenStreetMap data, and we have demographic data in this example. In order to support geospatial analysis, we use geoindexing. And for clarity, we did avoid here in this chart to show the time-based indexing, but both can be combined, and this allows you to do temporal and spatial analytics on the graph structure. And the architecture which is used to manage the data flows is shown here in this figure. On the left-hand side, you see 3 data domains. They expose functionality using APIs. and the data they use is shared using streaming topics in the backend. And exactly this is the point where our PyGeoCube hooks in. It can retrieve data from APIs and also from the streaming topics using standard protocols in automated procedures. And this automation is key to integrate across many different domains, and also to do this on a continuous way, to repeat the analysis and to do a steady study on an ongoing and ever-evolving field. So finally, the data is forwarded into a multi-layer graph, and this then is, in our case, the Tiger Graph database, which offers scalable algorithms for doing analytics. How such an individual layer is defined is shown here in this picture. We have a Sparkle query, and each of these Sparkle queries defines a layer. And this layer of data is added to the graph, and we can now use buffered data in local workspaces. And this solves the problem of missing availability or accessibility and technical limitations of public services. And the most important aspect is the automation aspect here. So by defining what a layer should look like, or how a layer should look like, we can automatically repeat the procedures and update the data and add new data slices to a layer on the fly in an automated way. As a result, we become able to do structural graph analytics on this Tiger Graph database. And the idea is to use projections, which is shown here. For example, if we have multiple different aspects, some positive aspects of a thing or of a system, and also negative aspects, we can now differentiate and isolate the aspects, or even combine them and bring the data together into a comprehensive view like it's shown here. The backbone of our data model is always the full picture, and then for some special analytics, we can simply project it and take out individual aspects like shown here. And now you can switch the context and manage multiple different facets during your analysis without losing the context for this purpose. So as an example of structural analysis, we show some word clouds. So for example, we loaded the data from OpenStreetMap, clustered it, and we found 8 clusters, and each of the individual clusters has a certain number of tags in it. And this is just one simple example for doing analytics on a structural level, but this is not all. We did not reach our goal yet. The idea is to go deeper. The idea is to go out and learn models to predict, for example, the neighborhood, to understand what is missing in a certain context or so. And different machine learning algorithms have one thing in common. They typically expect the data to be provided in a matrix form or in a tensor form. And all these tools out there, pandas, networks, and Keras, Spark, etc., they all share this property. So this means having the data in a graph structure is not really a good fit as an input for such data analytics tools. Hence, we say the idea is to formulate some transformations. We call those things projections, to project a certain context into a tensor. And this tensor then can be loaded into the machine learning algorithms. And so we combine temporal analysis, structural analysis in the graph, and also machine learning algorithms, which are out there. And we combine all these things together in this methodology to really do integrated analytics.
So what started out as a quest for sustainable decision support under the expectation of easy data asset integration and domain blending far too soon hit a reality of costs and effort spiraling out of scope. So we were not able to meet the fair data principles. But rather than to only address our problems, we have designed PyGeoCube to address the fair data principles and therefore address the fundamental way in how we can deal with issues of different data models and formats, accessibility, and most of all, automation across knowledge bases and knowledge domains. Our hope is that this tool can help us answer bigger questions on sustainability across domains businesses and societies, and allow everyone to easily share, blend, and analyze data at scale. And we think that would be fair. Thank you very much. We ran a little bit through that.
Thank you. If people want to add any questions to the Q&A feature or put anything in chat, that'd be great. I can start off a little bit. It seems like there's a lot going on, and I think people have asked, or someone just asked again about the slides, which I feel like is a common theme in like every session so far that I've are your slides already on Zenodo, or do you plan to upload them, or do you have another link maybe you could share?
It's uploaded already. It's in the system.
Okay.
It has been uploaded.
Okay. All right. So it's in. It should be in the system, so people can take a look at it there.
What the status?
We uploaded it to Xanadu. Yeah.
Okay. So I did have a quick question, unless someone else has something to ask. You're talking about like being able to take information from all of these open source, data sources and then combining them. And you were talking about layers specifically. So I kind of wanted to just clarify for myself. When you're talking about layers, is that something that's does it mean something concrete in the context of this graph, or is that more of like a conceptual way of thinking about it? Like you're thinking about dividing the information up into these sort of sections or groups. And I just wanted to kind of clarify that. Is layers like a feature of the application or the technology?
So it is. It's a logical to organize the data. Instead of saying, hey, I have stuff in files, I could split a large table into multiple files which represent parts of the full table, for example. So we logically slice the graph into layers. Technically, the data is just one graph. Our graph database does not give us namespaces. We do not, okay, there are different databases in the server, but the idea is within one graph, we want to be able to have a holistic view on everything we know in a certain domain, in the integrated domain for the research. And then we want to slice and dice the information into isolated contexts. For example, if I go to the geodata, I can ask what points on the globe are relevant for me for business and what is maybe for leisure. And I can now say, give me all the geo information about business locations and sports locations. And in one situation, I'm interested in both. And maybe in a different context, I need it separated. And hence, I filter away all the unneeded stuff to get a layer from my graph. But on the load side, it's different. I get data from one technical tool and feed this data into a layer so that I can handle where did the data come from and what's the structure. The mapping is done on the layer level as well. It's an organizational trick because the layers potentially contain information and eventually you do have to combine the layers. And this is not clear upfront how to do that. Sometimes you need to tune the algorithms and add weights or something like that to bring the layers into the right, into the right overlap, let's say it like this. And that's a conceptual thing.
So I don't want to take over all of the Q&A because there are a couple that just started, but just to clarify, it's like saying, we've got you mentioned like the geographical information, you mentioned like temporal information. Are each of those, would those be considered a layer of their own? And then when you ingest the data, you kind of defined, these are the things we're interested in for geographical info. These are the things we're interested in for temporal info. So you load those in. And then on the other side, for querying, you could do a combination, or you could say, I only want geographical information. Is that correct?
Right. Okay. And the typical query is something which gives me a data set, which then goes as input into machine learning algorithms. So typically the query is not yet the answer. It's only the state. So the graph becomes a staging area where I can do a meaningful combination of the data in a much easier way. Instead of doing ETL processes, I can do a proper query, and the query gives me the result, which is then the input for the analytics. And this makes research easier.
Okay, thank you. So we have one question here, or a couple now. How do you curate or choose the Sparkle endpoints you crawl?
Very good thing. That's the problem we have. We have to find out who offers the data. We need to investigate right now what is the quality of the data. In our case, we just went into the OpenStreetMap domain and found there is the Sophox service. It's a publicly available service, so other people run this service, and so we are very thankful to get access to the system and work with it. In other cases, we may have downloaded the full OSM dataset, converted into our own triple format, and run our own server like Sophox does. So this is a variety of different approaches. And the idea is to be agnostic, to have just an API endpoint, and either it understands the Sparkle query language, or in OSM, you have Overpass, which is a different query language, but conceptually our layer definition just has a query and an API endpoint. So we can combine any API which has a query language. Even Solar search engine could be used, for example. So there is no limitation here. It's very flexible.
It's basically you like almost an abstraction layer over, as long as you have a way to query it, whichever language you're using, and an API to get the data, you should be.
Exactly. And for the streaming data, we just hook into a topic, into a Kafka topic, and we simply assume that the data is in a certain format, in a certain JSON format, like a Sparkle query comes with a result set which has a certain structure. We assume the same structure in the Kafka topic, and if those things are corresponding, the implicit mapping happens on the fly.
So here's another question. How do you deal with access control when you pull data from APIs? You essentially circumvent all API business and access logic in this case.
In our case, we worked only with open datasets where no additional login mechanism is needed. Only open public datasets are used right now, but in the future it is planned to also follow OpenID and other authentication mechanisms.
Okay, we have another one. In the abstract of your talk, RDF versus property graphs have been mentioned. Can you please elaborate on that? When do you use RDF and when property graphs?
So the RDF graph is not directly used by us. We consume data which is represented by others in RDF graphs. So other people build their knowledge bases and their data sets, and they format the data using RDF. And then ideally, there is a Sparkle endpoint to load the data or to query that data. And once we get a result from such an RDF dataset, we convert the triples, we bring it into the property graph and build our layers. So we use RDF as the input, and then we bring it into the property graph because this is the format we need for the algorithms. Our machine learning algorithms couldn't work directly with the RDF graph, hence we do the mapping in between.
Okay, I don't see any other questions, but we do have a minute or two. If people have any, please feel free to add them. And is it okay if people reach out to you directly if they have questions they need to clarify, or just want to get in touch or whatever?
We are happy to answer any question, and also we are very happy to see collaboration and discussions in this field to improve it. It's not only about software, it's not about the tool itself, it's about the spirit behind data sharing, and we see a lot of demand here to integrate across domains.
Okay. Well, thank you. I don't see any other questions, so I think it's okay to stop unless you two have anything else you'd like to add.
No,
You're good.
Thanks for having us.
Yeah.
And
Okay. Thank you very much.
Thank
Bye.
you. Bye-bye.
Bye-bye.